Hi, Year 12. This is our third lesson for the topic of Statistical Analysis for Extension 1 Mathematics. In this lesson, we're going to learn about normal approximation of binomial distribution. So this is what we've covered so far: Bernoulli random variables and Bernoulli trials. And then we looked at binomial distribution, its mean and variance, and binomial probabilities. In the last lesson, we learned that the binomial distribution can look a lot like the normal distribution, and we looked at some of the conditions for this to be the case. We looked at different values of n and decided as n increases, the shape of the distribution becomes more normal. We also looked at different values of p and decided that when p is equal to a half, we have a symmetrical distribution. But when p is towards the extremes, so 0 or 1, we have a skewed distribution. Now, if you want to play around with this yourself, in Excel, you just create the following formulas in row 4 and then fill down. Now, you can see here that I have got 10 trials and my probability of success is 0.3. And here in column A, this is how many successes I have. Here's NCR, you can see the formula there. Here I've worked out the probability of success to the power of R, and here's the probability of failure to the power of n minus R, and then I have just multiplied these three together to get our probabilities. Then what you do is select the probabilities in column E and you graph them using a column graph. So here's 10 trials, probability of success 0.3, and we can play around with different values of P and note the difference in the graph. So here we've got probability of success 0.1. You can see how this one is not a normal distribution, but this one is approaching a normal distribution. Now, if you want to change the number of trials, you're going to need more rows. So you'll need to fill down your formulas so that you have the numbers from 0 up to 50. So fill it down to row 54 and then recreate your graph. And you can see now probability of success of 0.3. This is looking really like a normal distribution. And again, we can try different values for p, and even p equals 0.1 looks like a normal distribution. So how large does n need to be, and how close to 0.5 does p need to be? As a rough guide, if n multiplied by p is greater than or equal to 5, we can approximate a binomial distribution with a normal distribution. Let's check this out. So here we've got 10 trials, and we've got p is equal to 0.1, so 10 times 0.1 is 1. This doesn't look like a normal distribution at all. Here we've got 50 trials, still 0.1, 50 times 0.1, NP is equal to 5, and you can see how that is really starting to look like a normal distribution. So let's consider a binomial distribution X. It is binomially distributed, number of trials is 20, probability of success is 0.3. And we can see how we have got discrete data here being approximated by a smooth curve. And we would like to know what the mean and standard deviation of that curve is. Now, fortunately, on our reference sheet, we're given the mean and variance of a binomial distribution. So we can use those formulas to calculate them. So the mean will be 20 multiplied by 0.3, which is 6, which kind of makes sense. And the standard deviation, well, that's the square root of variance, so square root of NP multiplied by 1 minus P, which is 2.05. Now we know from the empirical rule that 99.7% of the data lies within 3 standard deviations of the mean. So let's calculate that. Let's do 6 take away 3 lots of 2.05, and then 6 plus 3 lots of 2.05. We've calculated that 99.7% of the data lies between negative 0.15 and 12.15. And that kind of looks right, doesn't it? And this is what we can write. Instead of this statement here, we write the normal approximation of X is distributed as a normal distribution with mean 6 and variance 2.05 squared. And we can use it to answer questions like this. Now, just think about it for a second. If we wanted to answer this question here, what's the probability we have greater than 7 successes? We'd have to use this formula if we were doing the binomial distribution. We'd have to calculate the probability of 8 successes, then 9 successes and 10. And remember, there's 20 trials here. I've only given you a snippet of this graph. It goes all the way up to 20. This would take us a long time to do via the binomial distribution. So a normal approximation saves us a lot of time. So let's have a go at doing these questions. We want the probability that x is greater than 7. So I'm going to use the z-score. Now x in this case is going to be 7, and the mean is 6, and the standard deviation is 2.05. Now you might be thinking, well, why are you using 7 when it's going to be greater than 7? And I'm going to talk to you about that in a second. Let's work this out. We have got z is greater than 0.488, and we're going to need to go to tables. So looking up 0.49, which is along here, that's going to give us that part there. So to get the bit in here, which is what I want, greater than 0.488, I'm going to need to do 0.5, take away this number, which is 0.31. But this one, probability that x is in between 4 and 7. So again, we're going to do z-scores. So 4 take away the mean divided by the standard deviation, and 7 take away the mean divided by the standard deviation. Working those out. Now, negative 0.98, that's over this side here, and we want in between there and the center. So that's actually symmetrical with looking up 0.98. So all the way over here. And this one here, 0.49, so that's above, just sitting in there, and we want it less than that. So looking up 0.49, that's up here. And then we're just going to add those two together. So the probability that x lies in between 4 and 7 is 0.52. But you might have picked up something there. I mean, it's not a perfect approximation, is it? And if we actually want to work out x is greater than 7, should we include 7? Like if we want greater than 7, maybe we should go from 7.5. And this one here, it says, please include 4. So include this one here, but don't include 7. So maybe we should go from 3.5 up to 6.5. Now what we're talking about here is doing a continuity correction. Now we can use a continuity correction if the data is discrete or if we're approximating a binomial distribution. But there's one other time we can use it. Back in Year 7 we learnt that discrete data only takes certain values, typically whole numbers, and it's often the result of counting, whereas continuous data is the result of measurement and takes all values. But here's an interesting fact. If measured data is rounded, then it's no longer continuous. A really good example of this is age, because we say, I am 16 years old. We don't say, I am 16 years and 8 months and 4 days and 7 hours, etc. So age is discrete. And so there's one other time we can use a continuity correction. That's with continuous data that is measured to the nearest unit. So let's return to our question from before, and this time we're going to use a continuity correction. When we work out the probability that x is greater than 7, I'm going to go from here, from 7.5. Okay, I'm not going to include 7 because there's no equal sign here. So with my z-score, I'm actually going to do 7.5 as x instead of 7. And with this one, I want x to be in between 4 and including 4, but less than and not including 7. So I want to include this. So I want to go from 3.5, so 3.5, up to, but not including 7, so up to 6.5. So you can see how I've put that in, 3.5 in for x here and 6.5 in here for x. So what's the difference? Well, here's the two questions here that we did without the continuity correction, and here they are with the continuity correction. And here's the actual probabilities. So remember I said that if we wanted to find out the actual answer, we'd have to use the binomial distribution formula. So I just did this quickly on a spreadsheet, worked out the probability of 8 successes plus 9 plus 10, etc., all the way up to 20. So it actually matches here with the continuity correction. But here we didn't have as big a range between 4 and 7, so the difference between without continuity correction and with was pretty subtle. And the actual probability was in between the two of them. Now, in terms of the syllabus, continuity correction is not mentioned at all. So it's up to you whether you want to use it. And the reason I'm showing you is because when you go and do past papers, in the answers you're going to see two solutions, one without continuity correction and one with continuity correction, and both are marked as correct. And speaking of the HSC, let's have a look at this question. An airline company that has empty seats on a flight is not maximizing its profit. An airline company has found that there is a probability of 5% that a passenger books a flight but misses it. The management of the airline company decides to allow for overbooking, which means selling more tickets than the number of seats available on each flight. To protect their reputation, management makes the decision that no more than 1% of their flights should have more passengers showing up for the flight than available seats. Given the management's decision, and using a suitable approximation, find the maximum number of tickets that can be sold for a flight which has 350 seats. So the first thing that I can see is that the probability that any passenger makes the flight is 95%. Now we're wanting to form a binomial distribution, and a binomial distribution is made up of Bernoulli random variables. So we're looking for a success-fail type situation. So can you see that that would be makes the flight, misses the flight? Now it doesn't matter if you make success making the flight or if you make success missing the flight, as long as you're consistent. I'm going to make success making the flight. So X, our random variable, is going to be the number of people who make the flight. And we are going to sell N tickets. So X is distributed as binomial distribution with N trials, and probability of success is 95%. So we want to approximate X as a normal distribution and then use the Z-score, but we don't know mu or sigma. But fortunately, on our reference sheet, we're given formulas for the expected value, or mu, of the binomial distribution and the variance. So let's substitute in what we know. Mu is equal to N times P, and P is the probability of success. Sigma is the square root of variance, which is equal to the square root of N times the probability of success times the probability of failure. And so we've gone from X being a binomial distribution of N trials, probability of success 95%, and here's the normal approximation. It has mean 0.95 N and variance 0.0475 N. Now we want to use a normal approximation because it's too much work to use the binomial probability formula to work it out any other way. So this is what we want. The probability that X is greater than 350 to be less than or equal to 1%. Now where did I get this 350 from? Here. There is a maximum of 350 seats on the flight. We can sell more than that, but we only want a maximum of 350 people turning up. Now we're going to turn this into a Z-score. By the way, if you want to use a continuity correction, then we would calculate probability that X is greater than 350.5. So we would want to include 350 because it's okay if exactly 350 people turn up, but we don't want more than that. And in your answer key, you'll see both answers. So let's use a Z-score. In this case, X is going to be 350. We know the mean and we know the standard deviation. So let's draw up a picture. We've got a cutoff of 350. On the day, we don't want any more than 350 passengers turning up. We want the probability that greater than 350 passengers is less than or equal to 1%. Now considering 1% here and 1% here, in between those two values is 98%. That's not one of our empirical rule values. So we're going to have to go to tables. And we kind of have to do it backwards because we know the probability, but we don't know the Z-score. Now having a look here, we've got all the way up to a particular point. We want 1% there, so we're looking for 99%, or 0.99, and somewhere in between these two, it's closer to this one, so 2.33, that's our Z-score. And so substituting 2.33 into here, I'm going to solve an equation rather than an inequality. Multiply both sides by the square root of 0.0475n, and now collect everything on one side. So 0.95n plus 0.507812 square root of n, take away 350 is equal to 0. Now the easiest way to solve this is to recognize it as an equation that can be reduced to a quadratic. We've got n and the square root of n, and this is a constant term. So I'm going to do a substitution. Let m equal square root of n. That's going to give us 0.95m squared plus 0.507812m, take away 350 is equal to 0. I'm just going to use the quadratic formula to solve that. So when we put that all into the calculator, you can see how I've only done the positive square root because m can't be negative. It is the number of tickets we're going to sell. I get 18.93. Now, the temptation would be to stop there, but remember m is equal to the square root of n. So in other words, n is equal to m squared, and so n is 358.3. We should sell 358 tickets. Okay, that's it for this lesson. Our last lesson on this topic is on sample proportions.